Okay, so get this. Imagine, like, scientific discoveries, but happening at warp speed, fueled by AI that can just analyze mountains of data like it's nothing.
It's incredible, right?
The key to this future, though, something most people haven't even heard of, AI accelerators.
Yeah, it's a bit of a hidden gem.
That's what we're diving deep into today. We're sifting through a stack of cutting-edge research, industry reports.
All that good stuff.
You ready to get ahead of the curve on this tech that's quietly changing the world?
Absolutely. It's already touching your life in ways you might not even realize. Like, think about it. Your phone, it unlocks with a glance, right? Or your smart speaker, it actually understands what you're asking it.
Right.
AI accelerators are a big part of that.
It's like having a secret weapon for AI, but instead of being hidden, it's hiding in plain sight.
Exactly.
So first things first, what exactly are these AI accelerators?
Okay, so in the simplest terms, think of them as specialized hardware, custom built to make AI tasks faster and more efficient than your typical computer processor could ever dream of.
Okay, so kind of like how a sports car is built for speed,
Mm.
these accelerators are built for AI.
Exactly. And you know how a race car needs a really powerful engine? Well, AI needs this specialized hardware to handle these crazy demands, especially with these massive language models like, what is it, GPT-3, the one everyone's talking about.
Because those things are huge EE, right? Like
Yeah, so
billions of data points.
billions, trillions even in some cases, parameters.
Mm.
Traditional processors just weren't designed for that scale. It's like trying to run the latest video game, on a computer from the 90s. It's just not going to be pretty,
Total system meltdown.
pretty much.
So what are researchers doing about it? How do you even begin to build an engine powerful enough for that?
Well, that's where it gets really interesting. You've got two main paths that researchers are exploring right now, digital and analog accelerators.
Okay, two totally different approaches. So let's start with digital. What's the deal there?
The digital accelerators are the most common right now. You've probably heard of GPUs, those graphics processing units. They were originally designed for like rendering graphics in video games,
Oh, yeah.
but it turns out they're also really good at the kind of math that AI relies on.
So they repurposed gaming tech for serious AI work. That's pretty clever.
It was a game changer, literally. And
Mhm.
companies like NVIDIA have really taken this and run with it. Their A100 GPUs, they're the workhorses behind a lot of these AI breakthroughs you hear about.
So are these digital accelerators getting even better, or have we hit a wall?
Oh, the innovation is constant. Researchers are always finding ways to squeeze out more performance. There's this one really fascinating approach called pruning. Imagine taking a giant neural network, like a massive network of roads, and then you streamline it by removing any roads that don't actually lead anywhere important.
So cutting out the unnecessary paths to make the whole system faster.
Exactly. And then you've got sparsity, which is about focusing on only storing and processing the most important data. It's like, instead of hoarding every single item you've ever owned, you just keep the things that spark joy. Decluttering for AI, basically.
Less clutter, more efficiency. I like it. Okay, so digital accelerators are already doing some pretty amazing things. But you mentioned analog accelerators, which, to be honest, sound a bit more mysterious. What makes them different?
So analog accelerators, they have the potential to be even more energy efficient. And that's a huge deal because training these AI models takes a ton of power.
Yeah, I bet.
One really promising approach uses something called SRAM-based in-memory computing, or IMC for short.
Okay, break that down for me. What in the world is IMC?
So imagine a spreadsheet, right?
Right.
But every single cell not only stores data, but can also perform calculations directly within the cell itself. You wouldn't need to move that data around for processing. It all just happens right there in the memory.
So instead of having to shuttle data back and forth between a storage unit and a processing unit, it's like having these mini processors built right into the storage.
Exactly. That's a great way to put it. It's a really elegant solution.
That's a pretty cool visual.
Yeah, it's what makes analog computing so potentially powerful for AI.
But I'm guessing there are some challenges too, right?
Yeah.
It can't be all smooth sailing.
Of course not. One of the big ones is noise. Analog signals, they're super sensitive to any kind of interference, which can really throw off those calculations.
Makes sense. It's like trying to have a conversation in a really noisy room. Sometimes the message gets lost.
Exactly. And then another hurdle is the needed for high-resolution analog to digital converters, those ADCs. They basically act like translators between this analog world and the digital world that computers understand.
So even if the analog calculations are super fast, you still need to convert those results back into a language that digital systems can work with.
Precisely. And that conversion process,
Yeah.
that can create a bottleneck.
Got it. So both digital and analog have their own pros and cons. Sounds like researchers are still trying to figure out the best way forward.
Yeah, you hit the nail on the head. It's not a one-size-fits-all situation. The exciting part is that we're really just at the beginning of this journey. There are so many different architectures being explored, and each one has the potential to unlock these new
It's
possibilities.
like we're standing on the edge of, like, a whole new frontier in computing.
Absolutely. And, just like the early days of computers, no one can say for sure what the most successful architecture will be.
Yeah, it's still early days.
Exactly. So that's why you've got all these different companies, right, trying out these wildly different approaches.
Okay, so walk me through some of these, like, wild approaches. What are we talking about here?
Okay, so you've got companies like Samanova and Grok. They're really making waves with these data flow architectures.
Data flow architectures. Those sound intense. What makes them stand out?
Okay, so imagine a perfectly choreographed dance, right? Where every movement just flows seamlessly into the next.
I like it.
That's kind of how these data flow architectures work. They break down complex AI tasks into these smaller pieces that can be processed simultaneously. It's like a well-rehearsed dance troupe,
Okay.
moving in perfect harmony. That's what makes them so efficient for those AI workloads that require a lot of parallel processing.
Okay, so it's all about optimizing that flow of information,
No.
making sure everything moves as efficiently as possible.
Yeah.
What about those massive chips we were talking about earlier? The ones that are like the size of a dinner plate?
Ah, you're thinking of wafer scale
Yep.
engines. Cerebras. They're really pushing the limits there. Their CS1 chip is literally as big as an entire silicon wafer.
Wow. Talk about thinking big. What's the advantage of going so large with a chip?
Okay, so think of it this way. A traditional computer chip, it's like a city, right? Lots of different districts, and they all need to communicate with each other. Data has to travel across all these different districts, and that can create bottlenecks and really slow things down. But with a wafer scale engine, it's like having the entire city on a single level. Everything's closer together, so communication is much faster.
So it's all about reducing those communication bottlenecks, allowing that AI to work faster, more efficiently. It's like having a high-speed rail system connecting all parts of the city. What other, like, cool architectures are out there?
One that really captures the imagination is neuromorphic computing.
Okay.
It's about designing chips that actually mimic the structure and function of the human brain.
Okay, now that sounds like something straight out of science fiction. Are we talking about artificial brains here?
Not quite artificial brains,
Okay.
but definitely inspired by them. These chips use artificial neurons and synapses
Wow.
to process information in a way that's more analogous to how our brains work. You've got IBM's True North, Intel's Loihi. Those are two examples of chips taking this approach.
So instead of just like mimicking the way we organize data in computers, they're trying to mimic the way our brains actually process information.
That's wild.
Yeah.
But it makes sense, right? I mean, our brains are still the most powerful computers we know of.
Exactly. That's the thinking. But it's also a massive challenge, right?
Yeah.
The human brain. Incredibly complex.
Oh, yeah.
We're really just starting to understand how it all works. But if researchers can crack the code of neuromorphic computing, it could lead to these entirely new types of AI
Yeah.
that are more powerful, more efficient than anything we can even imagine today.
Okay, I'm officially blown away. But before we get too lost in the future here, let's bring things back down to earth for a second. We've talked about performance, efficiency, but what about just like the practical side of things? How easily can these different accelerators be used to actually solve real-world problems?
That's a critical question. One of the key factors is programmability.
So can developers easily adapt these accelerators to different AI tasks, or are they stuck with the specialized hardware that can only do one thing? We don't want to end up with a bunch of one-trick ponies, right?
We need AI accelerators that are like flexible enough to kind of keep up with the ever-changing demands of the field. What else should we be thinking about?
Scalability.
Okay.
Can we connect multiple accelerators together to tackle even larger problems? Because the trend is clear, right? These
Right.
AI models are only going to get bigger, more complex.
It's like those sci-fi movies where they keep adding more power to the main deflector dish until it explodes.
Right.
But hopefully these AI accelerators won't explode.
Let's hope not.
Yeah.
But in all seriousness, scalability is crucial if we really want to push the boundaries of what's possible with AI.
So we've got programmability, scalability. Anything else we should add to our AI accelerator checklist?
Accessibility.
Okay.
Will these technologies be limited to those large companies with massive budgets? Or will smaller players and researchers have access to them? Right.
Because democratizing access to this technology,
Yeah.
that's going to be crucial for fostering innovation across the board.
Totally. We don't want to see a future where only a handful of tech giants control the keys to AI.
Exactly. Making these tools more accessible is key to unlocking the full potential of AI across all these different fields.
Speaking of unlocking potential, I read about a project, Gen SLM. It sounds like something straight out of a science fiction novel.
Yes.
Using AI to analyze just massive amounts of genomic data.
Gen SLM is a fantastic example of what's possible when you combine these AI accelerators with cutting-edge research. Imagine an AI model, okay, designed specifically to analyze these massive genomic sequences.
Okay, yeah.
We're talking about like the building blocks of life here.
And what does Gen SLM actually do with all that genetic data?
It can analyze those sequences and predict the evolution of viruses.
Hold on, this sounds incredibly complex. Are we talking about AI analyzing things like genetic data, medical scans, and patient histories all at once? Exactly. And not just for individual patients, but potentially for entire populations.
Wow.
This could lead to earlier detection of diseases, more effective treatments, and even preventive measures tailored to specific genetic predispositions.
Wow. We're talking about a whole new era of personalized medicine,
Heck.
all powered by AI.
And that's just scratching the surface.
Okay, my mind is officially blown. But with all this talk about like pushing boundaries, revolutionizing industries, I got to ask, who are the major players in this AI accelerator game? Who's building these like technological marvels?
Well, you can't talk about AI accelerators without mentioning NVIDIA.
Yeah.
They've been such a dominant force in this space for years, especially with their GPUs, though A100, for example. It's like become an industry standard for training these massive AI models that we've been talking about.
So NVIDIA is like the reigning champion, and
Yeah.
everyone else is vying for the title.
In a way, yeah. But it's an exciting time because you have some serious contenders emerging. We talked about Cerebras earlier, pushing the boundaries with their supersized wafer scale engine, that CS2. They're really like demonstrating that these alternative architectures can outperform those traditional GPUs for specific tasks.
It's like a David versus Goliath story, but with like silicon and AI.
Exactly. And then you've got companies like Sambanova, GraphCore, both forging their own path with those data flow architectures we were discussing earlier. Definitely names to keep an eye on.
So yeah, healthy competition, always good for pushing innovation. Are there any other like unexpected players in this race?
Well, you can't forget about the giants like Google.
Right.
They've developed their own custom AI chips, those TPUs,
Huh.
tensor processing units,
Right.
specifically designed for these machine learning tasks.
Of course, Google. Always building their own empire, brick by digital brick.
Exactly. And Intel's another big player. They acquired Habana Labs, a company focused entirely on AI accelerators. Now they have the Goya chip for running AI models and the Gaudi chip for training them.
Wow. So even like the veteran chip makers are jumping onto the AI accelerator bandwagon. It seems like everyone recognizes that this tech is the future.
Yeah, it's hard to ignore the potential impact. We're talking about advancements that could revolutionize healthcare, finance, climate science. The possibilities are pretty much endless. But as with any powerful technology, there's a responsibility to make sure it's used for good.
That's a really crucial point. It's not just about building the fastest, most powerful AI. It's about using it ethically, responsibly.
Absolutely. It's a collective effort here. Researchers, policymakers, industry leaders, and even the general public all have a role to play in making sure these advancements benefit everyone.
Yeah. It's like we're all part of this grand experiment, figuring out how to navigate the future of intelligence, both, artificial and our own.
Well said. That actually brings us to the end of our deep dive. We went from the inner workings of these AI accelerators all the way to their potential to reshape entire industries.
This deep dive has been a wild ride. I hope our listeners are walking away with like a sense of wonder about this technology and its potential to really change the world as we know it. Thanks for joining us on this incredible adventure into the future of AI.